Okay, so we are continuing our discussion of Fourier transform. Today we're going to go through the discrete Fourier transform, and then we'll look at the fast Fourier transform, and then we'll switch to just doing worksheet 4, like I said. We're going to start off, just considering a signal that has been digitized, meaning that it has been both sampled and in both time and amplitude. And it's been discretized in both time and amplitude. We'll call that signal, let's just say f, and it's going to be a vector dependent on time here, where n is going to be the index that we use to count. And so this is just equal to some vector f0, f1, f2, all the way up to, in this case, fn, big N, and give it a little transpose. And so we'll have big N points, big N plus 1 points. So the discrete Fourier transform is then defined as f under bar hat becomes a discrete function of omega, and this will be equal to the sum from n equals 0 to n of fn times e to the minus 2 pi times j times the quantity n m over big N, where again j is the imaginary constant. And actually this should have been omega m, not omega n. So when we do the discrete Fourier transform, we are switching from one index to another index. And then we can define the inverse Fourier transform to be f, which is a discrete function of Tn, equal to 1 over big N times the summation from little m equals 0 to big N times f hat n times e to the 2 pi j mn over big N. Okay, so the DFT is just a linear operator that maps the data points in f, which is in the time domain, to the frequency domain, and we call that f hat. And we'll add a little vector there. And so in general, you can represent this discrete Fourier transform using a matrix. We can call that big F with a double underline, such that we can just simply say that f hat is equal to big F times little f, just a simple multiplication of those matrix to a vector. And it turns out that this kind of computation is generally inefficient. It requires on the order of big N squared operations, and it just ends up being inefficient. And to overcome that, people have come up with what we now know and call the fast Fourier transform, or the FFT. So anytime you see a Fourier transform applied to some measurement or signal, people are almost undoubtedly using an FFT. Exceedingly rare that they would not be using an FFT. And so the most commonly used FFT is known as the Cooley-Tukey algorithm, which is basically a divide and conquer approach. You basically break down your DFT computation into different regions and then compute it separately for those rather than applying it to the entire system. This was just a generalization of the idea, or the general idea of the FFT was popularized by Cooley and Tukey in 1965, when they discussed this first algorithm that they came up with, and then it was later discovered that they had independently rediscovered an algorithm that Gauss knew back in 1805. So this stuff actually stretched all the way back to Gauss. All right, so the nice thing about the FFT is that in general it requires on the order of n times the natural log of, that should actually say n there, not 10, should say n because otherwise that's just a constant value you could just write out rather than a natural log of 10. For a signal, so it requires that many calculations for a signal with length of n, which is less than big N squared. And so just for a short example, if you take an audio signal measured for 10 seconds at sampling rate of 44.1 kilohertz, the resulting signal will have 4.41 times 10 to the 5th samples, and then you can just simply compute the number of calculations needed. So for the DFT, we have n squared, which is ends up being equal to 1.94 times 10 to the 11th, which is approximately equal to 200 billion calculations. And if we use the FFT instead, this is n times the natural log of big N, and that ends up being equal to 5.73 times 10 to the 6th, so approximately only 6 million calculations. And so thus the FFT here results in a speed up factor of around 30,000. So a massive speed up in the computational, or let me say that again, a massive reduction in the computational costs required to compute the Fourier transform. And so in worksheet 4, you're going to use the discrete, we're going to use the FFT, essentially.